So if E and F are dependent events, the probability of E and F is equal to probability of E times the probability of F given E occurred. So this is the probability of F given that E already occurred. So let's say I pick 5 students. What's the probability that their birthdays are each in a different month? Well, the first student, there are 12 months, and their birthday can be in any 12 of them. The second student, there are 12 months, but given the first one has their birthday in 1 month, there's 11 left. Likewise, for the third students, there's 12 months altogether, but there are only 10, given the other 2 occurred in different months. And the next one would be 9/12ths. And the last one would be 8/12ths. And you'd have to multiply that out to get your answer. Now, instead, if I ask, what's the probability that at least 2 are in the same month, well, then we could have 2 in the same month, or 3 in the same month, or 4 in the same month. There's all sorts of different possibilities. This would be the complement of all different months. And so it would be 1 minus the answer from the preceding question. But this brings us back to that idea that we had mentioned previously about permutations. And we said that permutations are arrangements of distinct objects there are no repeats, and order matters. And we'll look at those again in a couple minutes. Instead, combinations are arrangements of different objects there'll be no repeats, but order does not matter. And so let's look at a couple of examples. Let's say I have 4 students, A, B, C, D, and how many ways can I pick 2 of them to do 2 different problems on the board? Well, if the problems are different, order matters, and this is a permutation. So we could have A work on the first, then B, A on the first, then C, A on the first, then D. We could have B on the first, then A, B on the first, then C, B on the first, then D. We'd have C, then A, C, then B, C, then D. We could have D, then A, D, then B, or D, then C. There are 4 people to pick for the first problem, 3 for the second, so that gives me 12 ways. Instead, same 4 students, how many ways can I pick 2 of them to work together on a problem? Here, order does not matter, so this is a combination. So we could have A work with B, A work with a C, A work with D, that, well, B is already working with A, B could work with the C, B could work with D. C is already working with A and B, C could work with D. And we've already got D working with everybody else. So there's 6 ways. And please notice that the number of combinations is less than the number of permutations. So, to find the number of permutations, it's written, the author of your textbook uses this notation: permutation n objects, choose R. So if there are n objects, and we want to select R of them, they define it as n factorial over n minus R factorial. I always learned it as the product of n and all of the numbers less until I have R factors. So let's look at some examples. Let's say I have permutation 7 objects, choose 3. Using the author's definition, that would be 7 factorial over 7 minus 3 factorial, which would be 7, 6, 5, 4, 3, 2, 1, over 4 factorial, 4, 3, 2, 1. If you notice, those common factors divide out, so I'm left with 7 times 6 times 5, which are the first 3 factors of 7 factorial. And so that would give me 30 times 7 is 210. Instead, another example, if I wanted permutation 11 objects, choose 2, I could look at 11 factorial or over 11 minus 2 factorial and work it all out. Or I could say that I'm going to have the first 2 factors of 11 factorial, which gives me 110. Let's try one more. Let's look at another example. Let's look at permutation. Let's say we have 6 objects and we're picking 4. Again, we could look at that as 6 factorial over 6 minus 4 factorial and work it out. Or we could realize that that would give me the first 4 factors of 6 factorial. And so that's going to give me 30 times 12, or 360. Now, when we go and look at combinations, the author of your textbook uses the notation combination NR. A lot of other sources write it as N combination R. Sometimes you see it as N over R in big parentheses. And that's N factorial over R factorial, N minus R factorial. Or permutation NR over R factorial. So these are combinations if we're going to choose R from N, and order does not matter. And so let's look at some examples. Let's look at combination 7, 3, and using that first definition, that's 7 factorial over 3 factorial, 7 minus 3 factorial, which would be 7, 6, 5, 4, 3, 2, 1, over 3 factorial, 3, 2, 1, 4 factorial, 4, 3, 2, 1. Notice that the 4, 3, 2, 1 cancels out. And so this is where I get that definition of 7 permutation 3 over 3 factorial. And that would be 30 times 7, or 210, over 6, which would divide to 35. Instead, if I look at combination 11, 2, that would be 11 factorial over 2 factorial, 11 minus 2 factorial. Or I can think of that as that 11 permutation 2 over 2 factorial, which would multiply to give me 55. There's a relationship between your combinations and Pascal's triangles. And in Pascal's triangle, all the entries are combinations. Well, what does that mean? Pascal's triangle is 1, 1, 1, 1, add those, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. This is thought of as row 0. This is thought of as row 1. This is thought of as row 2. And so this first entry would be the combinations 0, combination 0, 0. The second entry would be the combinations of 1, combination 1, choose 0, combination 1, choose 1. This next one would be combinations of 2, combination 2, choose 0, then combination 2, choose 1, combination 2, choose 2, and so that each of these entries corresponds to the combinations. Let's backtrack a minute. I just realized that a couple of things that we did not mention. If we look at permutations, any number permutation 0, we'll always look at equal 1, and combinations, any number combination 0 will always equal 1. That goes along with the idea that no matter how many things you have to pick from, if you want to choose 0, there's only one way of choosing nothing. So let's